We're going to continue a theme of how do you take all this computing that comes about because of running AI, how do you address some of the bottlenecks that result from that? And I think our next talk is going to address dynamically reconfigurable processors so that you can allocate processors in an efficient way. So with that, I'd like to introduce our next speaker, Yoshio Sato from Renesas.
Thank you.
Yoshio.
Okay, everyone. My name is Yoshio Sato from Renesas. Today, I'd like to present about, it's called Dynamically Reconfigurable Processor Technology for Vision Processing. Okay, so let me start with who is Renesas. So probably you know it, but so Renesas is from Hitachi, Mitsubishi, NEC, Japanese semiconductor companies. And we have microcontrollers, microprocessors. So we have a good share in these areas. And recently we acquired, it's called Intercell and IDT. So we have also analog and mixed signal power discrete product lines. And also we have SoC and integrated platforms. It's called R-Car or R-In for automotive and factory automation. These are also, we have a good share in this market. Here, I'm responsible for, it's called RZ family. It is 30 to 64-bit ARM-based high-end embedded MPU. So image processing market, actually this page shows actually performance is driven by pixel size and also frame per second. So compared to like old camera like VGA 30 FPS, actually today we need to have like more than 100 times. And also if we consider the AI or inference, it's easily come to the like 2-digit, 3-digit, 4-digit performance improvement are required. In general, in overview, here we are talking about Embedded Vision Summit. We have a common challenge. We have restricted physical parameters like power consumption, but we have to achieve this kind of 3-digit, 4-digit performance improvement. This is kind of our common challenge we see that here. So today we have some solution or proposal. So, but before that, I want to revisit today's architecture. Maybe you might already know, but I want to expand today's challenge. So merge processors. So we are increasing CPU number, like dual or quad or octa that we are doing right now. And also dedicated IP. This is a neural network IP. In here, like yesterday, today we have several IPs expand like neural network dedicated IP. And also FPGA, we are heavily used FPGA for vision processing. Okay, so multi-CPU challenge is actually speed up is not linearly increased by the numbers of processors. So this is kind of common idea from Amdahl's law. For example, if we see the like 8 CPU case and parallel program portion is only 50%, speed up is only 2 times. And if program parallel portion is even 95%, speed up is limited about 6 times. So this is kind of common sense for the multi-CPU architecture. And also von Neumann architecture. This is also kind of important, like famous architecture, like memory load store architecture. So like CPU or DSP or GPU. These actually every time function we executed, then data have to move to DRAM every time. So this architecture is actually consuming power only for data transfer. So, and especially if we compare the internal memory and external memory, so external memory access, it have to go through the I/O buffer. Then it's like 128 times power consumption compared to internal memory access. So this is quite impact in this architecture. And the bottom side, I show the like wired logic architecture. This is like dedicated IP or FPGA. This is kind of pipeline type architecture. And this is reducing power by this memory access. So next, dedicated IP. So this is like typical case, new product, generation 1, we successfully launched. And generation 2, we need more function. And generation 3, we need more additional function. So, so functionality has to be increased product by product. And also cost and power is also increased. So, and next issue is dedicated IP. So generation 1, we successfully launched. Generation 2, unfortunately, we have bug, for example. So it's easily happen, and maybe you have experience. So in such case, because of time to market pressure, maybe we need to hide the such function, and also maybe then if we have chance, we respin the device. So if we found this kind of bug in the pre-production, somehow we can do the countermeasure. But what if we found a bug in the field? This will be more serious issue. So FPGA, for this kind of bug, it can be fixed because it's programmable and also like pipeline access type, so more or less power consumption. That's a good thing. But for FPGA, of course, we cannot utilize full area. There will be some free area. It's sometimes happen. And also adding new features may force move larger FPGA. That's a kind of common sense of FPGA. So then our proposal, it's called Dynamically Reconfigurable Processor. We call it DRP. So DRP is actually runtime reconfigurable hardware. It's combined with CPU flexibility and also dedicated IP or FPGA high performance. So let's compare that to the other architectures. For the CPU, it's running using ALU, so process 1 to a few operations in a cycle. And GPU, like Simdo engine, using parallel ALU, it's process 10 to 100 same operation in a cycle. And FPGA, this is pipeline processing and spatially expand various operations into a lookup table architecture. So DRP is actually combined with time-multiplexed and spatially pipelines. So this kind of pipeline is switching by cycle basis. So this is kind of DRP concept for the 2 dimensions kind of work in parallel. So let's see how DRP works in the system. So DRP is sit next to the CPU. It works as coprocessor. And also DRP support like memory to memory architecture from system external RAM. And DRP, there are 2 main portions. It's a reconfigurable processing element array and also fast and intelligent data mover. This is a DMA controller. So elements array, actually it's reconfigurable as pipeline circuit to fit with algorithm and run complex algorithm. So switching configuration within a nanosecond. So this configuration, we call it context. So algorithm will be mapped to the context. So we can support up to 64 context. And we also support programming with C language. So overall, DRP is like reducing memory bandwidth and achieve low latency. So this is more closer look about DRP hardware architecture. So DRP, it consists of a processing element array, and SRAMs, and the registers, ALU. And also there is, it's called STC, State Machine Controller, and DMAC. So the one set, we call it tile. So there are 6 tiles in the current DRP configuration. So this works as like flexible coarse-grained reconfigurable architecture. It supports binary and 8-bit, and tile-based scalability, 48 processor elements by 6 tiles, and we support intelligent DMA controller. So let's see how it works. So in the major portion, operational point of view, DRP, we can think about state transition and data path. So state will change by clock basis. Then a combination of state and data path is defined. Then based on the state change, data path will be also changed clock by clock. Okay. So then questions, maybe programming may be too complicated, but you don't worry about that. So we have a dedicated compiler. It supports like automatic synthesis from C to hardwired logic, and also automatic mapping from logic to DRP configuration. So as conclusion, we can support C to DRP mapping. Okay, so let me try how it works in the animation. So basically, algorithm can define as like state machine, finite state machine, and data path configurations. So this state start from state 1, and then data path 1 is selected. So data moves using this data path. Then next to move to state 3, then data path 3 is selected. Then data is going back from, for example, right to left. Then if same state is selected, keep the same data path. Then move to state 4. Then move to selected another data path. Then data move to from left to right. So like this, DRP works and support one algorithm. Okay. So the DRP, actually, there are two features to support reconfiguration. So one is, it's called dynamic reconfiguration. This is what I explained in the previous pages. So the other one is dynamic loading. This is this support new configuration in as little as 1 millisecond. So configuration is stored in the system memory. Then this configuration can be stored in the DLP, depend on the configuration. Then finally, we can support several configuration, and also we can support like bigger algorithms. So this is like benchmark result. We have two examples. One is canny edge detection and Harris corner detection. So DLP compared to CPU. CPU here is we use Cortex-A9 528 megahertz use case, and also DLP its maximum works at 66 megahertz. So it seems quite low frequency, but it means quite low power consumption. So we don't need like megahertz or like gigahertz, quite high speed frequency on DLP, even to achieve high performance. So for example, canny edge detection, like 12 times faster than CPU, and Harris corner detection is 20 times faster. Okay, so this page describes how it works as dynamic loading. So image is from camera input, then Bayer to grayscale using debayer, filtering, and then noise reduction is done by median filter, and canny is done by canny edge, then hysteresis judgment by using hysteresis threshold. So this is using the dynamic loading and changing configuration. Then we can achieve this kind of features. So this page shows an important point. So I said DLP has 6 tiles. For example, debayer, it can fit in the 1 tile. So 6 can be parallel this case. And medium case also 1 tile. And canny edge, these are 2 tiles used. And hysteresis threshold, it uses 6 tiles. So depending on the algorithm, we can manage, we can allocate how many tiles can be used. So this is an actual movie. So compared to CPU and DLP. So CPU, as you can see, there is little jitter, but DLP no jitter. So this is example how speed or how impact to the actual use case. Okay, so this is it's called A2M. This is our new product. This is first RZ product with DLP. And this device support, of course, DLP and large 4 megabyte SRAM on chip, and high performance HMI functions. For CPU, Cortex-A9 528 megahertz. This is actually heavy portion can be offloaded to the DLP. So this CPU can dedicate on a HMI function. So it can work in parallel. And also we support to the graphics accelerator and sprite engine. Sprite engines, it support like image rendering, not using RAM. Actually, it's directly map rendering from ROM interface. And MIPI CSI camera interface and JPEG encode decode, it support motion JPEG. And connectivity point of view, we support dual Ethernet, USB SDHI, MMC or NAND interface, and 8-bit DDR memory interface. This is support serial flash and even memory RAM interface. It's called hyper interface or octa interface. And high security EIPs like Arm Trust Zone. Trusted Secure IP this is Renesas proprietary secure IP, and hardware crypto acceleration, key management and storage, and access management. And we have several package options. So we are proud to announce this device, actually we got a product award from electronic product last year. Okay, so this is development tool support. We support software package. It bundled FreeRTOS version 10 and sample project, middlewares like device drivers, and also eScale Studio. This is Eclipse-based IDE, and also GNU compiler. And we are also preparing a sample project using DRP libraries. This is, for example, simple image signal processing. It supports image enhancement for fast and robust recognition, and also 2D barcode detection and recognition. It supports 720p resolution, 10 times faster than CPU, and iris detection and recognition. This supports 30 centimeter range, fast encrypted identity storage and transmission. So we are preparing this kind of sample project by using DRP. So evaluation kit, we include a CPU board, subboard, camera module, display output board, and JETA guys. Okay, summary and the next step. So embedded vision evolution demand more computing power and connectivity bandwidth. And available architecture have limitations, scalability, power consumption, flexibility, and efficiency. And DRP, we are trying to solve this problem with spatial and time-multiplexed computing. And today, I didn't talk about AI related, but actually we have roadmap for DRP technology to enhance embedded AI inference capabilities. So, and as Renesas, we are looking for partners who would like to work with our DRP technology. So if you are interested, please visit our booth and let's discuss. So these are technology resource for the support material. And we also have in our booth, we have a DRP demo. So please visit our booth and see how it works. Okay, thank you very much for your attention.
So if you have any questions for Yoshio, please step up to the mic.
Hi, thank you for a very interesting talk. From what I understand, the DRP works as a slave to the CPU.
Yes.
Is it also possible for to have a mode where the CPU can provide a service to the DRP and we can get these two bidirectionally communicating to achieve a task?
Yes, actually DRP can be the bus master. So it works as a coprocessor, so CPU and DRP can work parallel.
Thank you.
Yeah.
Okay, any other questions? All right, well, let's give Yoshio a round of applause. Thank you.
Thank you.